Hello everyone. In this video, we are going to discuss about the harmonic oscillations, which includes, more exactly, the equation of motion, the mathematical representation of harmonic oscillations with a second order differential equation and its solution of equation of motion. And in what way the solution can be utilized to explain the characteristic features of simple oscillations. So this is overall the concepts we are going to discuss in this video with this presentation. So first we'll try to understand the definition of simple harmonic oscillations. uh, Harmonic oscillations are basically, they are periodic in nature. Periodic in the sense it will repeats at a regular interval of time. If it is harmonic oscillations, that repeatness must be either in motion or in variation of any quantity. So you can define like is a motion or variation in which repeats at a regular interval of time is are harmonic oscillations. Such periodic nature mathematically exhibited by the trigonometric functions, which are sine or cosine functions. So that's why harmonic oscillations are mathematically represented by sine or cosine functions, because they are periodic in nature. And the characteristic features of a simple harmonic, uh, any oscillations are amplitude, frequency, and time period. In the frequency, in another way, we can explain with wavelength, because wavelength and frequency both are reciprocal to each other. So amplitude is the quantity, and this is a maximum displacement exhibited by any oscillator, and the displacement is always measured from equilibrium position. The maximum displacement from equilibrium position of an oscillator is amplitude, and the frequency is the number of complete oscillations per unit time. And of course, in any system of unit, the unit time is second. So you can define like number of complete oscillations per second also. The time period, the how much time the oscillator will took the how much time the oscillator will took to complete one oscillation is a time period. And you can correlate both frequency and time period with this relation. The frequency f is 1 by time period. And if you see the example for such harmonic oscillations are motion of a simple pendulum, oscillation of mass spring system, of vibrations of string in a guitar. And if you see the variation in any quantity is alternate current and electric and magnetic field components. These two will come under variation in here, either it may be current or voltage, and here the variation of electric field or magnetic field. So all these, either in motion or variation, all these will come under the examples for harmonic oscillations. So all these harmonic oscillations are can be classified into three. And of course, the classification is based on the force configuration on the oscillator. That oscillations are due to, which force is responsible for that. So if we choose the basis as force configuration, these oscillations are classified into three. The first one is free oscillations, or you can say simple oscillations or simple harmonic oscillations. And this is can also be called as ideal oscillations also. So all that sounds will same, the meaning is same. In four ways ways you can call these type of oscillations. And of course, we already told that the basis is force configuration. So the force configuration for free oscillations is only one. I mean, the oscillations are due to what? Internal force, or you can say restoring force. Internal force or restoring force. And rest of the two forces, which are dissipative force and external applied force, both will be equal to zero. So the conclusion, the oscillations are only due to internal force, are only due to restoring force, are free oscillations. But whereas damped oscillations, now the medium resistance force will come into picture, and we'll say that force is a dissipative force, or even you can say a resistance force offered by any medium. So along with this internal force or restoring force, one other force will also be responsible, that is dissipative force. But still, this external applied force is zero. So these oscillations are due to both these forces, internal force and dissipative force. And the third one, the forced oscillations are due to these three. These three forces together is responsible for the oscillations, are forced oscillations. But in this video, we are focusing only on the first one, simple harmonic oscillations. So we'll see that in detail. So now we'll change the definition from harmonic oscillations to simple harmonic oscillations. I already told you that the harmonic oscillations, which are only due to internal force, only due to internal force, are simple harmonic oscillation. See here, we are saying it is free oscillations, in the sense it is free from external forces. I mean, like dissipative forces, dissipative force, and external applied force. So that's why we are saying that is free oscillations. And we can say this is simple, or you can say simple because the force configuration is very simple, because rest of the two forces is zero. And these simple harmonic oscillations are characterized by these components. Yeah, I mean, in simple harmonic oscillations, the amplitude will never change. Irrespective of time, that amplitude will be always remains constant. Not only the amplitude, along with this amplitude, the frequency time period will also be same. I mean, we explained the previous slide. These three are characteristic features. Sorry, characteristic features of harmonic oscillations. So these three characteristic features will be remains same throughout the oscillations. And along with these three, the total mechanical energy will also be conserved. I mean, total energy will remains same. We'll see that in detail in further slides. And this motion is also characterized by the symmetric nature of that motion. Symmetric in nature, and that symmetry is with respect to a mean position. I mean, with respect to a particular point. So with respect to that point, the motion is symmetric in nature, and we'll say that point as mean position. Now we'll write the equation of motion for this simple harmonic oscillator, and further just see the diagram, which consists of three parts. So this middle one represents that oscillator is at equilibrium position, in the sense net force on that spring mass system is zero. If that mass is compressed, if that mass is compressed, what does it mean? You are displacing that spring, let be along the negative x direction. So if it is compressed and just release it, If you release that, um, don't apply any further force, just release that mass after compression. So now that a spring is tries to move towards the mean position, towards the mean position. But here you are not applying any external force, but still the spring itself is trying to reach the mean position. So that's why we are saying that is a restoring force. I mean, that spring mass system will try to restore its mean position. And whatever the force required to restore its mean position, that force is generated within the system itself. So that's why we are saying restoring force or internal force. And if you see that internal force, here we should mention that as FR, I mean restoring force. And this restoring force is proportional and opposite to the displacement. And this will be obeyed not only for compression, even if you stretch the string. I mean, let me here the displacement you are giving along the positive x direction. Let me just stretch the spring along the positive x direction. So when you release that stretched string, it will try to restore the mean position again it will try to restore its mean position. And here also that restoring force is proportional and opposite to displacement. And if you remove the proportionality and will replace this proportionality with a constant related to the spring, which is k. So this k is spring constant, or you can say elastic constant. So you can define this spring constant as magnitude of F by x. What does it mean? In order to displace that spring by a unit displacement, if that displacement is 1 unit, so in order to displace that spring by a 1 unit distance, how much force is required? That is spring constant. So generally the spring constant is a characteristic feature of a spring. So the restoring force is Fr is equal to minus Kx. So now we'll write that in differential form. So this restoring force is responsible for acceleration in the oscillator as per Newton's second law. So we can write this Fr is equal to, of course, minus Kx, and from Newton's second law we can write this Fr as ma. And we'll write this acceleration in differential form, d2x by dt square. I mean, because a is dv by dt, time rate of change of velocity, and again this velocity is time rate of change of position. So finally you get d2x by dt square. And just write this minus kx to the as second term of this second term of right hand side, so that you will get m d2x by dt square plus kx is equal to 0. And of course this is in differential form, but not in standard differential equation form. If it has to be standard, there should be no coefficient for this d2x by dt square. So that's why, in order to make this differential equation in standard form, uh, divide the mass on both sides, so that the first term will be d2x by dt square plus k by mx is equal to 0. But still it is not in standard form. Here the coefficient of this x must be some constant square. So that's why we'll replace this k by m with omega square. Omega, where this omega is angular frequency, or depending on the condition, even we can choose that as angular velocity also. Angular velocity also. I mean, why it is only this particular angular frequency and angular velocity? So that is chosen based on the dimensional analysis. I mean, I mean, um, if you see this K by M, K is which is F by X by mass. If you write the dimensional formula for this, dimensional formula of force is M L T minus 2. For displacement it is L, and dimensional formula for mass is M. So here mass and mass cancel, length and length cancel, and dimensional formula is T minus 2. So now instead of K by M, we need to choose a constant, and the constant must be having the same dimensional formula as K by M. I mean, the constant must be having same dimensional formula of T minus 2. So where this T minus with the dimensional formula T minus 2 is satisfying with for these two quantities. I mean, if you see, angular velocity omega is 2 pi f, or 2 pi nu frequency, and frequency is reciprocal of time period. So now 4 pi is a constant, so there will be no dimensional formula for 2 pi. So its time dimensional formula will be T minus 1. Then omega square will be dimensional formula with T minus 2. Now it is satisfying. So we can choose the angular frequency. Even angular velocity can also be considered, because angular velocity omega is angular displacement by time, or angle by time, and where this angle can be written as arc length by radius, arc length by radius. However, arc length is basically length, and radius is also length, and this is time. So now the dimensional formula will be 1 by t, which is t minus 1. So dimensional formula for omega square will be t minus 2. So both these two quantities, angular frequency and angular velocity, are satisfying the dimensional formula of k by m. That's why we can choose this omega as any one of these two. Now this equation is standard form, a standard differential, second order differential equation. So we'll say this is equation of motion. Equation of motion. What does it mean? What its significance? So this equation will explain the motion of the oscillator. Now apparently you can observe position of the oscillator is changing with respect to time. So differentiation is nothing but change in one variable with respect to another variable. And apparently it is, you can observe here the changing quantity is position of the oscillator, and this is changing with respect to time. But in what way it will change, that information we cannot obtain from this equation of motion. So in order to behavior of that position of the oscillator, in what way it will change, to understand that, definitely we need to solve this equation. You need to solve this equation, which is equation of motion. And for that, so this is the equation where we entered the standard second order differential equation. And we'll assume the solution will takes in this form: c x c e to the power of alpha t, right? So where this c and alpha are arbitrary constants in the sense, here it must be a constant, but what is its value we don't obtain, right now we don't know. So that's why we are not saying the particular constant. Arbitrarily there should be some constant value should be there. That is meant by arbitrary. So that x is equal to, let be, c e to the power of alpha t. And in order to obtain the solution, we need to differentiate this general solution to two times, because it is a second order. So its first order derivative will be, we already told that c and alpha are arbitrary constant. So the different so the c, constant c as it is, constant c as it is, and differentiation of alpha t is e to the power of alpha t is e to the power of alpha t, and differentiation of alpha t will be alpha. So first order derivative will be c alpha e to the power of alpha t, and its second derivative will be c alpha as it is, c alpha as it is. Differentiation of e to the power of alpha t is e to the power of alpha t, and differentiation of this alpha t is alpha alpha. So that final result will be c alpha square e to the power of alpha t. Now we'll substitute, we'll from this equation 2, 3 and 5. We'll substitute equation 3 and equation 5 in equation 2. If you do that, this d2x by dt square, which is equation 3, c alpha square e to the power of alpha t, and x is equal to c e to the power of alpha t. So these are the equations in previous slide. This is 5 and this is some 3, 3, right? And equation 2 is equation of motion d2x by dt square plus omega square x is equal to 0. Now you are applying this equation 3 and 5 in equation 2. If you do that, c alpha square e to the power of alpha t, which is d2x by dt square plus omega square as it is, x is c e to the power of alpha t. And if you observe both the terms, here c e to the power of alpha t. These two terms are common in both the terms. So if you make that common, c e to the power of alpha t, make that common, so that alpha square plus omega square is equal to 0. And now this is like a into b is equal to 0. So this will be satisfied either a is equal to 0 or b is equal to 0. I mean here either c e to the power of alpha t must be 0, or second probability is alpha square plus omega square must be equal to 0. But this cannot be 0. This cannot be 0 because this is general solution we consider. If it is 0, that general solution concept is meaningless. So c e to the power alpha t cannot be 0. So definitely this second term alpha square plus omega square must be 0, right? So the alpha will be what? Alpha will be what? Plus or minus I omega. If you see the solution like this, alpha square plus omega square is equal to 0. Alpha square is equal to minus omega square, and if you apply square root on both sides, alpha minus 1 square root is I, omega square root is omega, and two roots are possible, plus or minus. So of course it is second order differential equation, so we get two roots, right? So if we write the two roots as individually, so that x, first root, the first possible root to satisfy the first possible root to satisfy this equation of motion is c1 e to the power of I omega t. This plus one time, and second possible root is c2 e to the power of minus I omega t. Now this is second root. So two possible values are there to satisfy this second order differential equation. Now we will take the linear combination of both the roots, so that x is equal to c1 e to the power of I omega t and c2 e to the power of minus I omega t. Yeah, we given the solution for this, but it is in little bit complicated form. So we'll try to make this. Now our aim is to try to make this in simple form, so that you can use this solution in easy way. right? So for that, just write the expansion of e to the power of I omega t. I mean, this is like e to the power of I theta expansion is cos theta plus I sin theta. But here instead of theta, we have omega t. So if you write this expansion, C1 as it is, e to the power of I omega t is cos omega t plus I sin omega t. If it is e to the power of minus I theta, and here it will be minus. It means C2 as it is cos omega t minus I sin omega t. And if you see this, there are two real terms and two imaginary terms. So we'll group them separately. So just make the cos omega t as common for two real terms. So C1 plus C2 will be the remaining. And just common the I sin omega t for imaginary terms. So it will be C1 minus C2. And both these are, however, constants. C1 and C2 are constants. So the resultant of addition of two constant is also is also a constant. So for the sake of convenience, the addition of these two constants C1 and C2, for the sake of convenience, we will write this as A sine delta. And same way, subtraction of two constant will also give another constant. So this also, for the sake of convenience, I C1 minus C2, I of C1 minus C2 will write this as A cos delta. And we'll make this we'll change this I mean these modifications in this equation. So if you do that, instead of C1 plus C2, we'll write A sine delta, and instead of I sin omega t, we'll write A cos delta, A cos delta. Now, however, A is common for both the terms. And if it is common, this is like sin A cos B and cos A sin B. And sin A cos B plus cos A sin B is the expansion of sin of A plus B. So here the x will be equal to A sin of omega t plus delta. Now this is the final solution. And the solution is in simple form so that we can use in order to explain the motion of any simple harmonic oscillator. Right. Of course, this is a final solution for that equation of motion, but we should know each and every term in the solution. Then only we can apply this effectively. So if we see the each and every term of this equation, however, from the beginning we are saying this x is displacement with respect to time, displacement of oscillator with respect to time t. So we define the x and we define the t, time. And this A is maximum displacement, and we'll say that maximum displacement as amplitude. And we can justify that with dimensional analysis, I mean principle of homogeneity. This sine of omega t plus delta, right? This is like sine of some theta, whatever the term is there, this entire term will represent about theta angle. So generally sine theta will give, for any angle, the sine theta will give any constant value, right? So this entire term is constant. So if left side, I mean x is displacement, so definitely this A also has to be displacement. But this is maximum displacement, because the sine always oscillates between between I mean z minus 1 to plus 1. So either it will be minus 1 or plus 1, right? And the entire term of omega t plus delta is phase, or you can say angular displacement. angular displacement. I mean we can see that little bit with diagram. Let be this is simple harmonic oscillator, right? This is mean position x is equal to 0. Now after some time the position of the oscillator is somewhere here. And now you are explaining this position in two ways. One is linear displacement some x1, or in another way you can say angular displacement theta. So where this theta is omega t plus delta. So phase is nothing but position, but that is angular position. And omega is angular frequency. Omega is angular frequency, and delta is you can use this delta in two ways, either in phase constant or it can also be a phase difference. Depending on the condition, we need to choose either as a phase constant or phase difference. What does it mean by phase constant and phase difference? We'll see a little bit in detail. Little bit in detail. Let be this is a simple harmonic oscillator, a simple pendulum, right? When time t is equal to 0, the position of the oscillator is 0, right? And after some time t is equal to 0, now that oscillator is displaced by angle of 30 degree. So here the angular displacement is 30 degree. And after some time, this is t is equal to 0. This t is equal to t1 previously. After a time of t is equal to t2, it is linearly displaced by some x, angularly displaced by some angle of 60. And if you see, we will measure that angular displacement and linear displacement both from mean position. But it is not mandatory that our observation always starts from mean position. What does it mean? What does it mean? Let be a simple pendulum. Of course, that is mean position. I mean here the net force is 0, x is 0. But your observation is not started when that oscillator is at mean position, but your observation is started somewhere here. I mean you are starts observing that oscillator, it is already with an angle of some 30 degree, right? Now after a time of t1, after a time of t1, so of course this is mean position, but now our observation starts when it is already by 30 degree, right? What does it mean? Now our time t is equal to 0 here, because our observation starts if it is already at 30 degree. Now after a time of t, after a time of t equal to t1, now from this 30 degree it is displaced by some 30. So here that angular displacement theta is equal to omega t, which is 30 degree. But from mean position it is at an angle of what? 30 plus 30, because we need to measure the position always from mean position. So omega t is 30 degree, plus we need to add extra 30 because it is already at 30 degree, and we will take one more. So this is mean position. Of course the oscillator is already, I mean when we are starts observing, that oscillator is already with an angle of what? 30 degree. Now choose after some time t is equal to t2. T is equal to t2. After time of t2 second, it is displaced by an angle of 45 degree. I mean from 30-degree position to 45 degree, this is omega t. Omega t is theta equal to 45 degree. It is displaced by 45. But its position is omega t is equal to 45, and plus we need to add this initial value 30. Now see, if your observation starts from mean position, there is no issue. Whatever the angle is there, that will be its angular position. But if that oscillator is other than mean position, I mean when your observation starts other than mean position, we need to add this already, which is already displaced 30 degree consistently. Every time we need to add this constant, right? When we are adding this particular value, if your observation starts other than mean position, so we are consistently adding this 30 degree for each value. So this is delta, phase constant, right? So in conclusion, simply we can say delta is 0. What does it mean? Our observation start when it is mean position. Delta is not equal to 0 when your observation starts other than mean position. Right? If it is other than mean position, then by what angle it is already is there? That is delta. That is phase constant. And one more, the possible way to use is phase difference. And this concept is generally used when we are comparing two or more waves. To compare two or more waves, we use that same delta as phase difference. And for that, we'll take one example. First we'll draw the sine wave. We'll draw the sine wave because sine 90 plus 1. This is 90. This is 180. This is 270 and 360. This is sine wave. And we'll draw the cos wave also. We'll draw the cos wave. Cos 0 is 1 somewhere here. Cos 90 is 0. Cos 180 is minus 1. Cos 270 is again 0. And cos 360 is again plus 1. Cos 360 is again plus 1. Now this is cosine graph with cos graph. Now just observe the sine graph from 90 degree. Observe the sine wave from 90 degree. So from 90 degree onwards, now this graph is cosine. So what does it mean? The sine wave and cosine wave are differed by an angle of what? 90 degree. Or you can say pi by 2. So the phase difference between sine and cosine is 90 degree. So when you are comparing two or more waves, I mean by what angle they are differed. Under such condition, we use the delta as phase difference. Now we'll see the characteristic features. Characteristic features of simple oscillations. I mean these characteristic features includes position, or displacement, velocity, acceleration, kinetic energy, potential energy, frequency, and time period. We will try to explain all these physical quantities for simple harmonic oscillations. I mean, these are the characteristic features, both in mathematical representation as well as graphical representation also. So if you see the first one, which is position, or you can say displacement. So we already given that that x is equal to a sine of omega t plus delta. And let we'll consider, I mean throughout this presentation, let we'll consider whatever the observation we are making. Our observation starts when that oscillator is at mean position. When that oscillator is at mean position. What does it mean? So we are measuring that from 0. So delta will be equal to what? 0. So all that equations we are giving based on this condition. What that condition is? Your observation starts when that oscillator is at mean position. That is delta is 0. And for the sake of convenience, we'll write this same equation. I mean, of course, substitute this delta as 0 so that we'll get x is equal to a sine of omega t, or x by a is equal to sine of omega t. So this is position or displacement of the oscillator with respect to time, right? It is changing with respect to time sinusoidally. Now the second quantity, second characteristic feature of simple harmonic oscillations, which is velocity, velocity of the oscillator. And for this, first we will take that previous equation. Of course, x is equal to a sine of omega t, and the basic definition of velocity is time rate of change of position. Now use these two equations. I mean v is dx by dt, I mean d by dt of this a sine omega t. So differentiate this a sine omega t with respect to time. Of course, a is constant, amplitude is constant, so you can write that out of the differentiation. And if you do the differentiation, we'll get a omega cos omega t. Right now, sorry, this equation is velocity with respect to time. So velocity of the oscillator is changing with respect to time periodically. But the same velocity quantity, we can represent that mathematically, not only with respect to time, with respect to position also. With respect to position also. Right? For that, use this equation. Use this previous equation. X by A is equal to sine omega t. Then sine square omega t will be x square by a square, and cos omega t will be under root 1 minus sine square omega t. So that under root 1 minus the sine square is x square by a square. And if you simplify that, I am writing this directly, under root a square minus x square by a. So this is cos omega t. So sin omega t is x by a, and cos omega t is under root a square minus x square by a. Now just substitute this cos omega t in this equation, and if you substitute that, v is equal to a omega, and this cos omega t can be replaced with a square minus x square by a, and a will be cancelled. So this v is omega under root a square minus x square. So both are equations for velocity only, but this velocity is with respect to time. The first one is with respect to time, and this second equation, velocity with respect to position of the oscillator. In both the way you can calculate the velocity of the oscillator. And we will see the special cases of this velocity, both at mean position, both at amplitude. Mean position in the sense the x is equal to 0, and if you substitute that in that, omega under root a square minus x square. So this x is 0. So finally we'll get a omega plus or minus, which is maximum, which is maximum value. And at amplitude v is omega under root a square minus, instead of x again substitute a, so a square minus a square is 0, so velocity is 0, which is minimum compared to any other point. Sorry. So what does it mean? Let me take you take a simple pendulum. Now this is mean position and this is amplitude. Let be. Now this is the path of the oscillator. And if you calculate the velocity of the oscillator at at all the points, the maximum velocity value attained when that oscillator is at mean position. When that oscillator is at mean position, the velocity of the oscillator is highest, which is a omega. And it is having a minimum of velocity compared to any other point when it reaches to the amplitude. And here that velocity is 0. And the acceleration of course, which is time rate of change of velocity. And in this previous slide we already given the equation v is equal to a omega of cos omega t. So just substitute it, dv by dt. Of course a omega is constant, a omega is constant, so we'll write this as it is. Differentiation of cos is minus sine omega t, and differentiation of omega t is again omega. And if you rearrange this, omega into omega square, so a omega square minus sine omega t, and I can write this as a as minus omega square x, because just see here, this is minus omega square a sine of omega t, and this is x. Right, now this equation both in terms of, I mean with respect to time and even with respect to position also, in both the ways you can represent the equation in both the ways. And even for this acceleration also, we'll calculate the acceleration in two special cases. One is at mean position and one is at amplitude. So a is minus omega square 0. So acceleration is 0. And this is minimum compared to another point. But whereas at amplitude, a is equal to minus omega square a, and this is maximum. So acceleration of the oscillator is maximum when it reaches to the amplitude, and it is minimum when it reaches to the mean position. So both are contrast. I mean if you compare the maximum and minimum velocity and acceleration, both are contrast. So till now we just given the mathematical representation of these three quantities: position, velocity and acceleration. Now we will try to explain that in graphical way also, and we'll explain that with a single graph. I mean we'll include all the three plots in single graph so that you can compare that easily. So we will take common y-axis. Now for three physical quantities, three x-axis, right? One is for position, the second one is for sorry, velocity, and third one is for acceleration. So x, second graph is for sorry, velocity, and third graph is for acceleration. And on x-axis common time. So first we will write the equations for these three quantities. X is a sine of omega t, and velocity is a omega cos of omega t, and acceleration a is minus omega square a sine of omega t. And for the sake of convenience, and you will draw that for one complete cycle, because it is periodic in nature. After one complete cycle it will repeats again, the same will be repeats again. That's why no need to draw that for number of cycles. It is sufficient to draw for only one cycle. And if you see, these are periodic functions, sine and cos. So that one cycle quantity is a 360 degree. I mean, the periodicity of this trigonometric function is 360 degree. So it is better to close at 360 only. I mean, for one complete cycle. And for the sake of convenience, I mean, in order to distinguish these three quantities, we'll first divide that into four segments. Four segments. I mean, you are dividing that 360 into four parts. Right? So this is 90 degree, 180 degree, 270 degree, 360 degree. So we just drawing that for one complete cycle. Or in another way, like pi by, even it is, you can write pi by 2 or pi radian, 3 pi by 2 radian, 2 pi radian. Now first we'll draw the graph for sine, sorry, position or displacement. So this is basically sine graph. So simply you can draw the graph of what? Sine. Sine 90 is maximum, 180 is 0, 270 is minus 1, and 360 is plus 1, 0 again. And what is the maximum value of x? Generally maximum value of sine is plus 1, but its coefficient is a. So that's why this is the highest value, minus a on one side, and this is plus a at second side. So this is maximum displacement. So this is maximum displacement a. And similarly for velocity, it is cos function. So we'll draw the cos graph first. Cos 0 is 1, cos 90 is 0, 180 is minus 1, 3 pi by 2 is 0, 360 is again plus 1. The maximum value of cos is plus 1, of course, plus or minus 1, but it is with the coefficient a omega. So this highest value is maximum velocity or a omega on both sides. This is plus a omega at one side, and this is minus a omega at other side. And the third graph, this is also basically sine graph, but now this sine is multiplied with what? Minus. I mean, sine 0 is 0, so there will be no change, no much difference. Of course, sine 90 is 1, but it should be multiplied with minus 1, so you get minus 1, 0. And sine 270 is of course minus 1, but it should be multiplied with what? Minus. So it will positive value, and 360 is 0. So just negative of sine graph. And here this is maximum at one side, which is omega square a, and this is maximum at other side, omega square a. So this is graphical representation of position, velocity, and acceleration. Now we'll move to the fourth physical quantity, which is kinetic energy. And of course, the general equation for kinetic energy is of mv square. So we already proved that velocity of the harmonic oscillator is omega of under root a square minus x square. So just we'll substitute in this equation, and if you substitute that, k is equal to 1 by 2 m of, instead of v, write this omega of under root a square minus x square whole square. And if you simplify that, the final equation will be kinetic energy is of m omega square of a square minus x square. So now this is equation for kinetic energy of the harmonic oscillator. Now we'll see the special cases, both at mean position as well as amplitude. So at mean position, Ke is of m omega square of a square minus, instead of x we'll substitute 0. So it will be of m omega square a square. So this is maximum compared to any other point. If that oscillator is at mean position, it is having the maximum kinetic energy. And at amplitude, kinetic energy is of m omega square a square, instead of x a, so it will also be a square, and this is 0, and this is minimum. So that oscillator is having minimum kinetic energy if it is at amplitude. So this same behavior is exhibited by the physical quantity velocity. So velocity is also maximum at mean position and minimum at amplitude, because it is came from this equation, which includes this velocity. Now the fifth quantity, potential energy. So generally potential energy is stored, the work done is stored as potential energy. From that statement, the equation for potential energy is minus integral f dot dx. But we know that restoring force Fr is equal to what? Minus kx. So if you substitute that minus kx instead of F, this minus and minus will be multiplied and will be plus. So kx dx. However, k is constant. So you can write out of the integral 0 to x, 0 to x dx. And integration of x is x square, with the lower limit and upper limit 0 to x. And if you substitute that, the final will be half m omega square x square. And this is contrast to kinetic energy. Kinetic energy is maximum. Kinetic energy is maximum when it is at mean position, right? And kinetic energy is minimum when it is at amplitude. But potential energy is contrast to kinetic. Potential energy is maximum when x is at a, and potential energy is minimum when x is 0, and it is at mean position. Now, similar to like displacement, velocity, and acceleration, now we'll show the graphical representation. So first we'll try to show the graphical representation of kinetic, and then we'll move to potential, right? So for that, I mean, for easy understanding, we'll take the simple pendulum. X is equal to 0, and it is oscillating between x is equal to a and x is equal to minus a. Now we'll draw the graph. On y axis, kinetic energy. On x-axis, position of the oscillator. The position of the oscillator is in between x is equal to a to x is equal to minus a through this main position. And equation for kinetic energy k is of m omega square of a square minus x square. So just distribute this of m omega square for both the terms, of m omega square a square minus of m omega square x square. However, this first term is constant, some c, minus this half omega m omega square is also constant. So I'll say this is c2 and this is x square. Let me this is c1, which is equal to what? Kinetic energy. Now kinetic energy is taken on which axis? Y axis. This is constant. For the sake of convenience, I will write this c2 as 4a. And this is displacement is taken on x axis with square. Now see here, this is equation for what? Parabola. But this is with minus, so you'll get inverse parabola, but already constant is there. So what does that mean? This parabolic behavior is decreasing with respect to position from some constant value. I mean, this is c1, this minus is indicating it is decreasing in parabolic way, right, to amplitude. So this is graphical representation of kinetic energy, and we discussed in earlier slide, kinetic energy is maximum when it is at mean position. Kinetic energy is zero when it is at amplitude. Similar way, now we'll draw the graph for potential. Same, x is 0 between x is equal to a to x is minus a. So on y-axis, potential energy, and this potential energy is with respect to displacement. Displacement is from x is equal to a to x is minus a. And if you see the equation for potential, of m omega square x square. So this potential is taken on y-axis. Let be this is 4a, and this displacement is taken on x-axis. It is with square. This is a perfect parabola. So the behavior will be a perfect parabola. Just contrast to kinetic energy. So potential energy is maximum at amplitude and minimum at mean position. Minimum at mean position. Contrast to kinetic energy. And we'll do one more thing. We'll plot that same. We'll plot that both in single graph. I mean, I mean, so we'll take common y-axis, both kinetic energy as well as potential energy on y-axis, and on x-axis, displacement of the oscillator. In between, x is equal to a to x is equal to minus a. So now we'll draw the graphs first. For kinetic energy, this is inverse parabola. And for potential energy, it is perfect parabola. Perfect parabola. So this must be at same height. So if we include both the kinetic energy and potential energy single graph, and we can observe two special points. This should be same, should be on same line actually. So both the graphs are intersecting at two positions. What does it mean? For this, the y-axis is same. What does it mean? Just if you see that in detail, if I choose main position, if I choose main position, kinetic energy is maximum, but potential energy is zero. What does that mean? They are not same at main position. And if we choose amplitude at amplitude, now kinetic energy is minimum, but potential energy is maximum. What does it mean? Both are not equal at amplitude. So everywhere the kinetic and potential energy is not equal except these 2 points. Except these 2 points. So both the graphs are intersecting. Their kinetic energy is equal to potential energy. But what is that position? At what position both will be equal? Right? So what is that question now? So if we need to find the position of the oscillator. Under which condition? If kinetic energy is equal to potential energy. So both will be equal at what position, that we need to find out. And solution for this question is itself in the question, because we are finding that x under this condition. So just we'll substitute that both the equation and equate them. For kinetic energy of m omega square of a square minus x square, and potential energy of m omega square x square. Now this of m omega square on both sides will be cancelled. So remaining will be a square minus x square is x square. So that 2x square is equal to a square. So x square will be equal to a square by 2. So x will be equal to what? A by under root 2 plus r minus. What does it mean? So that positions are, one is a by root 2 is 1, and other side minus a by root 2, or approximately we can say x is 0.707 of a. If you take one example, like if amplitude is at 1 centimeter, so kinetic energy and potential energy will be same at 0.7 approximately 0.7 centimeter. So both will be equal. So that is the significance of this intersection of these 2 points. Now we already said that the characteristic features of a simple harmonic oscillation, there the simple harmonic oscillation will follow the conservation of total mechanical energy. So what does it mean by this conservation? I mean, this statement is energy neither be created nor be destroyed, but it will change from one form to another. And here that change of forms are kinetic and potential. Right? We'll try to prove this so the total energy will be remains constant. So for that, So I'm taking that graph which was explained previous slide. So I'll divide that into I will choose three different points, one, two, and somewhere. I mean to say, um, one is at mean position, and two is at amplitude, and three is at somewhere at x. Right. So we'll try to calculate kinetic energy, potential energy, as well as total energy at these three positions of the simple harmonic oscillator. So first we'll go to point 1. We choose this point 1 at x equal to 0. Sorry. What does it mean? At mean position. So first we'll calculate kinetic energy. And equation for this of m omega square of a square minus x square. At mean position, this x is equal to what? 0. So that equation will be of m omega square a square. And at that same point, potential energy of m omega square x square is the equation. And at mean position, this x is 0. So potential energy is 0. Now the total energy, which is sum of kinetic plus potential. However, the potential is energy is 0 at mean position. So here it will be of m omega square a square. And with this calculation, what is the conclusion? If that oscillator is at mean position, if that oscillator is at mean position, the total energy is only due to kinetic. The potential energy contribution is 0. And the total energy is how much? Of m omega square a square. Just remember this because we require this for further explanation. So total energy of the oscillator is of m omega square a square. Now we will choose the point. We choose that point 2 here. Point 2. What is that point 2? Amplitude. What does it mean? X is equal to A. X is equal to A. Now at x equal to A, we'll calculate kinetic energy as well as potential. Kinetic energy equation of m omega square of a square minus x square of m omega square a square. Here we choose that x is at amplitude, so a will be x will be a. So a square minus a square, the kinetic energy is 0. And potential energy of m omega square x square is the equation. And if we substitute of m omega square a square. Now the total energy, which is the sum of kinetic plus potential energy. And at amplitude, the kinetic energy is 0. So final equation of m omega square a square. And previous calculation and now this calculation. I mean at mean position and amplitude, the total energy is coming to the same. But the difference is at x equal to 0, potential energy is 0. But now at x equal to amplitude, the kinetic energy is 0. Right? This is the difference. Now, in detail analysis, we will take one more point. So somewhere here at some x in between mean position to amplitude, somewhere at x, point 0.3. What does it mean? That x is some random value of x. Now we calculate kinetic energy of m omega square of a square minus x square as it is, and just distribute that of m omega square a square minus of m omega square x square. So here the kinetic energy is non-zero. Similarly, potential of m omega square x square as it is. Now calculate the total energy, which is sum of kinetic energy plus potential energy. And if we substitute of m omega square a square minus of m omega square x square, this is for kinetic, and potential is of m omega square x square. So both will be cancelled. The remaining of m omega square a square. Still we are getting the same equation. The total energy is same, of m omega square a square. What does it mean? That simple harmonic oscillator is following this conservation law. The total mechanical energy of the system is not changing, it is always same. So there will be interchange of kinetic and potential, that's it. But however, the total energy will be remains always same, right? And what does it mean? We'll try to explain that little bit in detail. I will take different positions. I'm just taking with random values, not exactly, just for the sake of understanding. Kinetic energy, potential energy, and the total energy. X is equal to 0. Let be amplitude is 10 meter, 0 to 10. At mean position, kinetic energy is maximum, let be 10 units, but potential energy is 0. At amplitude, kinetic energy is 0, but potential energy is maximum. If you see, the total energy in both the cases same, 10 and 10. Now we'll take displacement at 1 unit. Now kinetic energy will decreases 10 to 9. The kinetic energy is only decreased, but it is not destroyed. So the decreased kinetic energy will change toward potential energy as 1 unit, because this total energy should be same, right? So here it changes, it is changing from one form to another form, I mean kinetic to potential. And if it is at 2 units, it will be 8. So there is decrease in kinetic energy, but at the cost of increase in potential. But however, total energy will remain same until that amplitude. So gradually that kinetic energy is decreasing and at the cost of increasing potential energy. But however, total energy will remain same. So there will be no change. This is meant by a conservation of energy. And this is obeyed by the simple harmonic oscillator. Now, sixth physical quantity, time period. I mean time taken to complete one oscillation. So in order to write the equation for time period, we'll take the displacement of the oscillator equation. X is equal to a sine of omega t plus delta. Here we'll do one thing. Instead of t, I mean you are replacing the t with t plus 2 pi by omega. Let's see what will happen. If you do that, x is equal to a sine, just distribute this omega for both omega t plus, here this omega and denominator omega will be cancelled, 2 pi plus delta. Now this is like sine 2 pi plus theta, I mean sine 360 plus theta, right? It will repeats after 360. Sine 360 plus theta, sine 2 pi plus theta is again sine theta, because it will repeats again, right? So x is equal to a sine of sine 2 pi plus theta is theta, so sine of omega t plus delta. Again you are reaching to the beginning equation, same. But at what cost? If you replace that t, I mean it is added with 2 pi by omega, and again you are reaching to the same point. So what does it mean? The time period t is equal to what we added for extra for t, 2 pi by omega. So this is 2 pi by omega, time period is 2 pi by omega. So this is generalized equation. This is generalized equation for any simple harmonic oscillation. I mean, irrespective of spring mass system or simple pendulum or torsional pendulum, whatever. The generalized equation is 2 pi by omega. If it is spring mass system, we already defined that omega from this omega square is equal to k by m. Now this is generalized. Now this is specific. This is specific. For spring mass system, omega, we consider this k by m as omega square. What does it mean? Omega is under root k by m. So final equation is 2 pi under root m by k. So this is generalized equation. This is specifically for spring mass system. Right? If it is a simple pendulum, this omega will be equal to under root L by G. So that it will be 2 pi under root G by L. So omega is 2 for simple pendulum, time period 2 pi under root L by G. Right? So omega is under root G by L. So just try. I explain this once again. Just see that. This is generalized equation for any system. This is specifically for spring mass system. This is specifically for simple pendulum. So it's just simple. Just substitute this omega value as per the physical system, then you will get exactly the time period for that particular system. And for the seventh physical quantity, frequency, which is of course mathematically reciprocal of time period. So we already given the equation for time period, 2 pi under root m by k. So if you substitute that, nu will be equal to what? 1 by 2 pi of under root k by m. This is equation for frequency of the simple harmonic oscillator. So these are the characteristic features. So now we'll conclude that. So through this presentation, we just focused on general equation of motion of simple harmonic oscillations, and then we given the solution for the simple harmonic oscillation as x equal to a sine of omega t. And by using this solution, we explain the characteristic features of this, 7 characteristic features of this: displacement, velocity, acceleration, kinetic energy, potential energy, and the sixth one is time period and frequency. Right? This is about a simple harmonic, basics of a simple harmonic oscillations. Thank you.